So first we're going to go over question 3, where we're looking at the two different first order reactions, A to B and R to S, both happening inside the same catalyst. The slab is very thin, it's just 0.1 centimeters thick compared to the surface dimensions of 2 centimeters by 2 centimeters. So you would want to treat diffusion as one-dimensional across the thickness and ignore the edge effects. Both reactions are irreversible in first order. The effective diversities of A and R are the same, and the surface concentrations of A and R at the outside of the catalyst are also equal. That means any difference in effectiveness factors and concentration profiles inside the particle come purely from the different rate constants K1 and K2. Under the given conditions, reaction 1 is faster with K1 equal to 4K2, and we were told that its internal effectiveness factor is 0.5. The effectiveness factor measures how strongly the diffusion is limiting the reaction inside the particle. For the first order reaction in a slab, you would want to use the Thiele models of reaction. In part A, the goal is to find the effectiveness factor for the slower reaction 2 when K1 equals 4K2 because the modules depend on the square root of K. If K2 is 4 times smaller than K1, then the Thiele modulus for reaction 2 will be half of that. So I set, as we can see here, that equal to the square root of K2 over K1, which then gave us 0.958. Plugging this into the formula, or the same slab formula, so then you would get the you would get this here, where you would get this is equal to the tangent of 0.968 over 0.958, and then this gives the higher effectiveness factor for the reaction 2, which does make sense physically since reaction 2 is slower. There's less consumption of R near the external surface, so the concentrations of R stay more uniform throughout the particle, and diffusion is less limiting when sketching concentration profiles. Negative L to positive L, A has a steeper drop from the surface to the center because it reacts faster, whereas R has a flatter profile because it reacts more slowly. Both profiles are systematic about the center within the center with zero gradient at x equals 0. And then for part B, we use the relationship to match the given effectiveness factor to the correct Thiele modules from the list of options, and then evaluating is equal to the tangent and then h, and then for each candidate it shows the different ones, which gives very close to 0.5, which is equal to 1.915, which is correct. For the reaction 1, that tells us that reaction 1 is in a moderately diffusion limited, but not negligible diffusion, but extremely severe either way. This value is what I then used in parts A and C for the given thing. For part C, it shifts to a different condition where reaction 1 becomes severely diffusion limited with effectiveness factor of 0.05. Again, for the slab, we use the same exact equation that we found above here. That means an effectiveness factor of about 0.05 corresponds to a Thiele modulus around 20, which is what I used. And then we know the Thiele model 1 and the effectiveness diversity and half thickness of the slab, so we can solve for the new rate constant K1 using the definition that I wrote out here. Rearranging gives us the K1 is equal to, and then subtracting, you would end up getting K1 is equal to 1.60. So these conditions, the kinetics are fast, but because diffusion is so limiting, only about 5% of the catalyst volume is effectively used, which is exactly what the very low effectiveness factor would be telling us. For question 4, I modeled the first packed bed reactor, R301, in the ethylbenzene production process using Polymath and then compared my results to the stream tables found in the textbook appendix. The reactor carries out 4 reactions involving benzene, ethylene, ethylbenzene, and byproducts like diethylbenzene and other hydrocarbons. I started by writing the general mole balances in terms of the molar flow rates and the reactor volume. Using the form dFi over dV equals Ri for each species, the reaction rates were written from the kinetic expressions given in the design problem, including the fact that the reaction 3 is reversible, so that the rate had both a forward and reverse term. To handle the reverse direction properly, I followed the approach from exam 1, where the equilibrium constant was obtained from thermodynamic data and combined that with the forward kinetic expression to get the net rate. Because the reactor is adiabatic, temperature changes along the bed due to the heat of reaction. To model this, I used an energy balance that relates the temperature gradient to the sum of the heat effects from the reaction. Polymath, I wrote an ODE for dt over dV that looks like the sum of reaction rates times their heat of reaction divided by the total heat capacity flow of the mixture. The heats of formation and the heat capacities needed to compute delta H were taken from the property table provided within the exam, which gave delta H and Cp for benzene, ethylene, ethylbenzene, diethylbenzene, and the other components. I kept everything in the required consistent units. And then for most species, I treated Cp as a constant with temperature to keep the model simple and stable for polymath, knowing that Aspen uses more detailed temperature-dependent correlations. I also included a pressure drop equation along the packed bed instead of assuming constant pressure. I implemented the packed bed correlation we used in class. That equation depends on gas density, viscosity, diameter, and the void fraction. I expressed the variables so that polymath could update the pressure and density as temperature and composition changed. At the inlet V equals 0, I used the flow rate, temperature, and pressure given in the stream tables for R301 speed. All components listed in the stream table were included in the model, even the insert or non-reactive ones, so the total flow and heat capacities were consistent with the real process. Once the system was set up for each of the species, molar flow rate plus 1 for T and 1 for P. I ran polymath over the reactor volume or catalyst weight corresponding. From the outlet flows, I calculated benzene conversion and the selectivity of ethylbenzene to the undesired products like diethylbenzene. Then I compared my polymath outlet values in reactor outlet temperatures to the corresponding values in the textbook. The trends match. Benzene is largely converted. Ethylbenzene is the main product. Some diethylbenzene and other byproducts form. The temperature rises due to the exothermic reactions, and the pressure drops along the bed. There were noticeable differences between the polymath results and the Aspen values reported in the book, just because the differences were based on just modeling assumptions. First, Aspen uses a detailed thermodynamic passage and real gas behavior, while my polymath model just assumed ideal gas and mostly constant heat capacity. So my temperature and equilibrium predictions are a little bit less accurate. Second, my implementation for the reversible reaction may not match Aspen's exact equilibrium constants or activity conventions, which can shift the distribution between ethylbenzene and heavier byproducts. Aspen can also include phase equilibriums, whereas my model treated the system as a single gas phase with no condensation, which affects both composition and heat capacities. If a second phase actually does appear, I think that the polymath model still captures the core, what was needed to be done, although the values that we did find obviously were a little bit different from the Aspen, which was going to happen just because it does run on a little bit of a different system. And then there's the overall energy balance, the pressure drop, the kinetics, mole balance for everything, and then the heats of formation in the CP, and then obviously the initial conditions, constants, and then just the differential equations, the pressure drop, energy balance, and then the independent variables that were used.